স্যার এখানে এফএক্স গ্রাফ মানে কি ফোর্স বাই এক্সটেনশন গ্রাফ স্যার?
Yes.
আর স্যার এখানে হাফ কে এক্স স্কোয়ার, স্যার কেটা কি স্যার কনস্ট্যান্ট?
Spring constant.
ওকে স্যার।
Hooke's law থেকে যেটা আমরা পাই।
স্যার
হ্যাঁ বলো। বলো ওকে বাকি।
স্যার আব্দুল্লাহ বলতেছিল যে আপনি কি ওদের কালকে একটা মেকআপ ক্লাস নিতে পারবেন নাকি?
কখন? 7:30টায়। হ্যাঁ না 5:30টায়। হ্যাঁ
5:30।
so the gradient of the stress strain graph within the elastic proportionality limit. So as long as the stress strain graph of a certain specimen is linear, the gradient of that linear segment is what we call Young's modulus, which is basically the ratio of these two quantities. For metals, we have such a big deformation region, which is a very large plastic region here. This E point represents the elastic limit, which is slightly inside the curve. So this is the part of the deformation that we call to be elastic region. And this is the part all the way up to the breaking point is what we call defined as a plastic region. One other interesting thing is that if we ever deform an object beyond the elastic limit, the object is going to start to gain some permanent deformation within itself. That permanent deformation is such a deformation that even if we remove the total deforming force, the object is going to have some deformation left within itself. So how much deformation will be left within the object? That can be found out by drawing a parallel line with the original OP section or this linear section. Let me explain why. Let's say we have deformed an object by applying, let's say, this much stress. So we have applied force, more load, and we have a deformed an object up to this much. And then we start to unload the object. So which means we start to remove the loads and we allow the object to get back to its original shape when the force would be applied 0. What's going to happen? The object is going to start getting back to its original direction, original dimension. It's going to try to get back to it, but it cannot do this all the way because the object has been deformed beyond the elastic limit. Some deformation would still be remaining within the specimen. And how much deformation would be left? That can be found out by drawing a parallel line, which is parallel with its OP section over here. So this line, if I'm drawing somewhat, this is parallel to this part, then the object is going to come back to this much shape, and this is the part that is going to remain within the object that we define as permanent deformation.
Sir, parallel, sir, কতটুকু হতে পারে? মানে what's the distance to which you have to hold parallel, sir?
Till it reaches the x-axis, because this is a stress axis. Stress is given by force over cross-sectional area. The cross-sectional area of an object can never be 0, obviously. So if we ever have to reach to this 0 point of the stress axis, this essentially means that the applied force has to be 0. Applied force, which is vice versa, equal to the elastic force developed within the object, or which you define as the elastic force or resistive force. So when the stress value is 0, then the object will reach a state of 0 stress. So that's achievable when the full graph will cut the x-axis. So the
Sir,
reason these
Sir,
are
where do we actually start considering that, like this parallel line? From the bottom or from the top? And if so, how do we know? Oh,
the starting point of the choice of the starting point of this point is somewhat like this. For example, let's say the point from where we start to unload the object. Let me give a very specific example, which might make sense. Let's say we have a setup over here. We have a bit of a clamp and we have a metal specimen, which has some measuring techniques of meter rules and fiducial markers placed beside. I'm just drawing a very rough figure, and then we have some loading mechanism over here. We can measure the length of this object. So let's say initially there is no load, so we start the graph of stress versus strain from this point. And then as we are going to slowly start to add more and more load, this marker is going to slowly go down and down and down. So if we start to plot the points, we're going to start to get a graph that looks like this. So there is going to be a very significant portion till which the graph is a straight line. And then the graph is going to start bending like that. And then the graph is going to start carving out like this. So anywhere, let's say, if you are making up this graph, as you slowly keep on doing the experiment, for example, let's say you have a computer software that's going to give you this graph of stress versus strain, where you simply are going to input the value of this reading from directly manually, and then that graph gets generated automatically. So let's say we load the object up to this much stress. So we are continuously applying load over here, and the object is getting bigger and bigger deformation. The object is the specimen is deforming more, which means the object is becoming longer. Let's say we load the object up to this much point, and then we decide for good measure, we decide for the experiment sake, we decide that now we're gonna start unloading the specimen. So if we now start to unload the object, so what's gonna happen? The stress value is gonna start to decrease from this point downwards, because whenever we're gonna reduce the F, the cross-sectional area remaining the constant and the constant to be constant, and the stress will become lower. So that from that point, this returning graph is gonna follow a track which is gonna be parallel to the original straight line part of the Young's modulus. The reason is that by overcoming the elastic point or deforming the object beyond the elastic point, this elastic point is the proportionality. Whenever we are deforming an object beyond the elastic limit, the object will start to undergo permanent deformation at atomic level or molecular level. But the object is still very much made up of the same material, which means no matter how much you bend it, bulge it, curve it, it is still the same material, which means its Young modulus is still very much the same Young's modulus. So whenever we're going to start to unload the object, it will, by virtue, will essentially maintain the same Young modulus as is. So that's why the object can start to come back to following the same parallel line. For not same, I shouldn't use the word same. Following the parallel line that is parallel with the original linear part of the graph. And eventually, whenever we remove all the load, so the stress value drops all the way from here all the way down to here, and eventually we reach a zero stress value. That's when the object is gonna hit the bottom line over here, and it's not gonna be deformed any further, because you are no longer applying any force, and the amount of permanent deformation can be founded by the x-axis intercept.
so sir, it's basically fully dependent on our choice, as long as the string or the material is within its plastic region.
Precisely. So if we deform the object, or if we load the object all the way up to the E point, which is the elastic point, and start removing load anywhere from that. For example, if we load the object up to this much stress value and then start removing the load, then the graph is gonna be produced like that, and the returning graph is gonna be exactly the same. If we do it from here, same thing. The graph is gonna be produced like that, and the returning path is gonna be exactly the same. If this exact return would be available all the way up to this E point. So this is the point that we define as elastic point. Up to this much point of the graph, the deforming shape and the returning path would be exactly same. But anywhere beyond this point, the object cannot get the original shape back. So it means the object is gonna follow somewhat of a parallel line, and it's gonna represent some permanent deformation.
Sir, what are we calling this tiny, length of the x-axis?
This is the strain axis.
Sorry, sir, strain axis, like what are we calling this region you highlighted, sir?
Which part?
I mean, sir, you said this is what is this thing you?
Oh, sorry, I moved. I mark করো.
When I said this part, this is permanent deformation you wrote over here, but did
Yes.
you name anything over here?
Whenever we are going to unload from any part, the object is going to immediately come back. For example, if I start to unload from here, we are going to have this much permanent deformation. If we start to unload from here, we are going to have this much permanent deformation. This is what we call permanent deformation, or we can say, because this is on the strain axis, we can say this is permanent strain.
Okay, sir. Thanks, sir.
No problem. আরেকটা জিনিস হচ্ছে যে if you have a permanent strain, and then that is definitely going to have some permanent dislocation of the particles within the object, and that dislocation means that we would have actual displacement of some of the particles from their original position to a new position. That would require some work, and that amount of work or slash elastic energy or plastic energy, or you can say deformation energy, would be stored within the object as work done. How much work is done, that can be found out by the area covered within this graph. For example, what I'm trying to mean, let's say we have a specimen, this one, and we applied this object up to this much load. Let me use red for this case. Let's say we stress the specimen up to this much point, and then we started to unload the whole specimen. So as we unload the specimen, eventually we get to this point on the x-axis, and the object is going to have some permanent deformation. For example, let's say initially the object was this much long. Let's say after we reach up over here, the object without the effect of under any force, let's say the object is now this much longer. So this much is what we call defined as permanent deformation. So how much work was done to achieve this permanent deformation, that can be found out by the area within this slice. This slice area basically gives us the amount of energy that is stored within this specimen. But if we are going for a stress strain graph, this actually gives us a stored energy per volume. Because what I showed you over here with a little bit of calculation, that if we have a look over here, that here, if we try to calculate the area under the stress strain graph, which is going to be half of L sigma 12, I actually wrote the half considering it was calculated within the triangular part, but this half doesn't essentially have to be a half. This is just a geometric constant. If you're trying to calculate, if you're trying to calculate it out using integration, then you can have a variable of equation. You can have, if you have trapezium, we can have other formula. We can so this half is basically numerical constant, so we can disregard this one's effect. Practically what we're trying to do, we're actually multiplying these two axis variables. One is the stress, the other one is the strain. So if we do multiply these two variables, you can see that stress is expressed as force over area. So this is this one, and extension and strain is given by extension over length. So if I do multiply these two variables, force into extension, this is basically the applied force multiplied by how much movement, practical actual movement of the load application point happened. So this force into displacement in the direction of the force can be considered to be the work done. And area, cross-section area multiplied by the length, can be essentially considered to be the volume. So the reason I'm trying to show you this, disregard the presence of the half over here. This is just a geometric area-based constant. So the point that I'm trying to highlight here is that area under the stress strain graph actually gives us this thing. This actually gives us the work done per volume of specimen, or I can only say work done per volume, or it can also say, we can also say that how much it also, or in other words, we can say that it is the energy stored per volume of the specimen while it is undergoing permanent deformation. So that's one thing. If this same graph was drawn for a force extension axis without other than the stress strain graph, then this would be called only energy. So if we had this same specimen, if we under the same experiment, if we were only plotting force versus extension, sometimes extension is represented by x, sometimes it is represented by e. So they are somewhat alternately used. So if you ever feel confused, feel free to ask me. But I'm going to be using both of them in appropriate cases the way that I'm used to. But both of these two letters, extension e, can be represented by e, or sometimes is also represented by x. So if we plot the same graph within the force extension graph, we're going to have the same, exactly same shape. So we're going to have the exact same shape. So let's say, oops, this goes on like that. Plus these are proportionality point E, these are elastic point E, and somewhere over here we have this in just a second. And then if we start to unload from this point, we're going to have a parallel line which is going to be parallel with this part over here, and eventually we can have this much permanent deformation or this much permanent extension. So if this part is, let's say, over here 2 centimeter, and this axis is plotted in centimeter, we're going to get exactly 2 cross of cutoff over here. So just a second, I mean, I'm going to take your question, just give me a little bit of time. The way we talk about the energy amount is actually the area under the graph. So one of the things that I need to understand, whenever we are applying the loads over here piece by piece, the object is becoming longer. The object is becoming longer. So we are applying more force, the object is becoming longer. So it is undergoing deformation. In this process, elastic energy is getting stored within the specimen. So if I ask you ever, let's say, when the object was deformed up till this much point, how much elastic energy is stored within the specimen? When the object was deformed up to this much point, how much elastic energy was stored within the specimen? That amount would be the total area under this much curve. So if you consider all the way up to this much curve, a curve under total যতটুকু area থাকবে, so under মানে হচ্ছে in this case the area that is covered between this line and the length axis or the deformation axis. এই গ্রাফের under যতটুকু area আছে এই পুরোটুকু হচ্ছে elastic energy stored when the object is deformed up to this much point. If we go fast, so this is the loading curve, so I'm going to label this as loading. If you go further, let's say if we go all the way up to over here, then you have to draw a much bigger area. So, and then in that case, all of this much area would be the energy stored within that specimen. So as we slowly deform the object, as we slowly extend the object, we have to input more energy. We have to do more work to make further deformation possible. And that amount of deforming energy will be stored within the specimen. That's for the loading part. Whenever we do unloading, for example, that the part that I'm represented over here by this dotted line of the return path, let's say we chose to unload the object from this point. Now, when the object will be unloaded, then we're going to be slowly taking loads out, and the force, the elastic force is actually working this way. So let me just use a different arrow. The elastic forces are working this way. So if we remove some load, this whole thing is going to actually start to go slightly upwards because we are removing the deforming force. So in that case, work would be done by the existing force of the system. So work will be given out, or energy will be left out from the system, energy will be leaving from the system. So as the object is going to be coming back to its original shape, so it's going to follow this path. So let's say I'm going to give an arrow over here and label this as unloading. So this is the unloading path, and the object follows this much path to while unloading. Then how much energy would be given up while during the unloading process? So if we unload it all the way up to zero deformation, then the total amount of energy that will be given out in the unloading process is going to be the area under the unloading graph, which is basically this much triangle. So you can see pretty well that this whole blue shaded area was the total amount of energy that was stored within the specimen while it was extended, and while we were unloading, the amount of energy that was given out is also the area under the unloading graph. And the remaining slice, which in this case is this much, maybe I'll shade this by black now. This remaining amount of area, this amount of energy basically represents that amount of energy or elastic energy, plastic energy, or you can say the deformation energy that is stored within the specimen that is causing it to undergo the permanent deformation. Yes, your question?
Sir, আপনার সেটা আনরিলেটেড বাট আপনার বুকলেটের সাথে যে টেস্ট পেপার গুলো আসছিল ওগুলো কি করব?
এগুলা মকের সময় যেভাবে টেস্ট দিতা, প্যারেন্টস সুপারভিশনে পরীক্ষা দিবা, পরীক্ষা দিয়ে তারপর সেগুলা ছবি তুলে আমাকে পাঠাবা।
কোন সাবমিশন ডেট আছে?
কালেক্ট করে নি স্যার এগুলো।
We don't have any definitive submission time frame yet, but you can start appearing them as at your convenience. We have all the individual chapter wise or worksheet based question paper, so you can take preparation for one full chapter and sit it at your own convenience. I think you're gonna have at least one more week to finish up all the papers. I'm not gonna give you individual date that this is the last date for this paper, this is the last date for this paper. I'm gonna say that maybe I'm gonna declare this on Tuesday, maybe, because Tuesday we're gonna have all the people present.
It is actually collected,
I might actually say that when it be the very last date to submit all the papers. In the meantime, I'll try and set up a Google Classroom where document sharing should be easier for all of us. Google Classroom is good for document sharing, right?
Yes, sir.
Yes, sir.
Okay, ঠিক আছে।
অনেক ভালো।
I'll definitely look it up and go for that. Salman, if you haven't collected it, Feel free to collect it. It's still available in the coaching. Mamun has it all.
And sir, can you sir to leveling করে দিবেন sir একটু মানে blue is the energy for the extension of the string during the loading part. Red is the
I'll label
energy.
these parts. I'll label these parts and then I'll make sense with you. Let's say I'm gonna give certain points over here. This is O. This is P, this is E. These are the points of the curve. Let's say this is a point that is A, this is a point that is B, this is a point C, and this is a point D. And let's say this is a point that is, do we have a E over here? We already have a E. This is a point that is F. Okay. So I have marked defined areas over here. So let me tell you this part. OB over here represents the loading curve. এই পার্টটা বুঝছো কিনা?
Yes sir.
OB represents the loading curve. Area under the loading curve represents the energy stored within the specimen while loading was being done. মানে হচ্ছে মনে করো অবজেক্টকে আমি এই পরিমাণ ফোর্স দিয়ে ঝুলায় রাখছি। এই কন্ডিশনে ওই এক্সটেন্ডেড অবজেক্টের ভিতরে কতটুকু এনার্জি স্টোর করা আছে সেটা মেজার হচ্ছে এই পুরো ব্লু এরিয়া। সো দ্যাট উড বি রিপ্রেজেন্টেড by the closed area covered by, let's say, O, B, C, O. So if you follow this path, O, B, C, O, this whole area represents the energy stored when the object was deformed up till point B, area under the loading curve. Now, if you start to
Energy stored for the loading part.
energy stored within the specimen while loading, or area under the loading part, loading curve.
Okay, sir. Yes sir.
Then if you decide to unload it from the point B, so in that case, the BF is going to be our unloading curve. So BF is going to be the unloading curve. In this case, it's going to be straight line, but we're still considering it to be defining it to be curve. It's supposed to be straight line, but for some specimen, it apparently gives a little bit of curve right over here. I'm not getting into that detail right now because that's a part of discussed in the properties of chapter, properties of matter chapter.
BF sir.
BF is your unloading curve, which is a straight line. BF,
Okay.
this line, B through F. This is the unloading curve, and the area under the unloading curve is basically the energy given out while unloading. So which is gonna be, let's say I'm gonna label this as BFCB. This triangle. Although it's a triangle, but still I'm using 4 different letters just to define the whole region. So BFCB gives you the total area that represents the energy given out while unloading. So whenever we're unloading, the specimen will be releasing energy. Then the area of the whole slice that remains within, which is the black shaded area, I can label this as, let's say, O, P, B, F, O. So if you have a look over here, O, P, E, I skip the E and A point over here. So O, P, B, FO. So the area of this slide, this is the amount of energy or plastic energy stored within the specimen, which caused the permanent deformation. এই এনার্জি আইডিয়াটা বোঝা গেছে কিনা? আমি যদি খুব বটম লাইন হিসেবে বলি, সিম্পল পার্ট হিসেবে বলি, area under the force distribution graph represents energy. While loading or while deformation is happening to a specimen, energy will be stored within the specimen. While unloading or object is trying to come back to its original dimension, force is getting removed or load is getting removed, the object is gonna give out energy. So in the process of loading, the object is gonna store energy, absorb energy. In the process of unloading, the object is gonna give out energy. If the object cannot reach back to its original dimension, some amount of energy would remain stored within the object permanently, which we call the deforming energy, which is equal to the slice of the area, that is the difference between the loading curve area and the unloading curve area. এইটুকু হচ্ছে পুরো গ্রাফের ডেসক্রিপশনের শর্ট ডেসক্রিপশন। Does it make sense so far?
Sir, one more question, sir.
Please.
From B to F, some energy is given out, sir, right, sir?
From B to F, yes, energy is given out.
And the but sir, you also said that BOFO. So within this part, there is some additional energy that causes the plastic, that makes the specimen a plastic material. So where does this energy come from? where does this energy comes from? Within the period, it is stretched, sir.
Yes, precisely. You can see that the area under the OB curve, which is basically, let's say, this whole blue shaded area, this is significantly bigger compared to the red shaded area, right? So let's say the blue shaded area, maybe let's say the blue shaded area, let's say is 100 joule, and maybe the red shaded area represents only, let's say, 70 joule. This can happen. I'm not very precise about the area. This is just assuming this in the area numbers. But obviously, the blue shaded area by visualization is definitely bigger than the red shaded area, right? So
Yes, sir.
in the deforming process, we are storing more energy within the specimen compared to the amount of energy that we're getting back while the object is becoming unloaded. This is basically why the object can store some energy within itself, so which is given by the black shaded area, which we are calling the stored energy or the deforming energy, which is basically 30 joule, something of that sort. Yes,
Yes, sir. Thank you.
no problem. Anyone else? Any further question?
No, sir.
আচ্ছা, এই এরিয়া ক্যালকুলেশন গুলো বোঝা ইম্পর্টেন্ট হচ্ছে এরকম যে এই জিনিসগুলোর উপর বেস করে খুব সিম্পল এমসিকিউ কোশ্চেন হয়. If you understand it properly, it's very easy to answer those questions, and you can very easily choose out the section or segment that is the correct response, or the line that represents the loading, the line that represents the unloading. It's actually pretty simple, but if you don't understand it properly, it can be very confusing. Sometimes this graph can be also represented pretty much like the way that I've discussed to you in the earlier class, that these force extension graphs can sometimes also show up in force length graphs. So if it is shown up in force length graphs, in that case, this is simply going to be starting off from an x-axis cutoff point where this much represents the original length. But the rest of the part pretty much remains the same. As the object is going under deformation, loading curve, the object is going to store energy. If it is allowed to come back from within its elastic limit, it's going to come back to its original deformation, original point. In that case, the object is going to have no permanent deformation whatsoever. So there will be zero stored energy after all the forces are removed. That's basically what we call an elastic deformation. But if the object is allowed to if the object is unloaded beyond the elastic limit, some amount of energy would be stored within the object because of the permanent deformation. So force versus length graph হলে আমরা এই সিমিলার একটা সিনারিও পাবো, বা সেখানে সব ঘটনাগুলো হবে হচ্ছে একটা এক্সিস ইন্টারসেক্টর পরে, বিকজ এই পার্টটুকু রিপ্রেজেন্ট করবে হচ্ছে অরিজিনাল আনএক্সটেড লেন্থ. That can also happen. The other variation that it can also happen for this kind of discussion is whenever we have a compressive scenario, which is not very detailedly discussed in your syllabus, but sometimes the CIE teachers like to test your understanding for a reverse scenario. So it's easier for you to visualize a compressing scenario if you try to consider it for a spring. For example, if you have a spring that is of a natural length, let's say a spring is clamped to a roof, it's possible that we can pull it down to make it extended. Then we can also push it upwards to make it compressed. So the spring is going to store energy in both way. So if a certain object starts to become compressed, one of the things that you have to understand that this I have described as force versus extension graph. In this case, this extension, we use the term force extension graph because this is easier for us to visualize and is the most commonly used term pretty much not only in physics, also in engineering as well. But this extension variable doesn't exclusively represent extension. This can also represent compression as well. Now, the reason the term force extension is more common compared to force deformation is because whenever objects are compressed, there is a certain point when the objects tend to behave incompressible. I mean, let's say you have a piece of metal. If you are trying to push it really hard without impact load, let's say you are trying to continuously increase it, for example, like a hydraulic press. Okay, there is a certain limit beyond which pressing it would become pretty much impossible. I mean, you can theoretically think of an infinite amount of pressure, but it's physically impossible to achieve. So pretty much in all cases, if we are trying to compress a certain specimen, there comes a certain point where a very large amount of increase of force would give us very little deformation. For example, if I try to represent this, one of the thing, just try to consider a physical example. These are the this stuff that I'm discussing to you to give a understanding for how to visualize things. For example, if you consider the basic structure of a spring, let's say this is a spring where we have coils of wires making the spring. Okay, we have gaps in between the coils of wires, which makes sense. So we can extend this spring, and there is elastic limit and there is a proportionality limit, and beyond a certain point, if we extend the spring too much, it is not going to come back to its original shape, blah, blah, blah. Perfectly good. But what's going to happen if we start to compress the spring? This is the part that is pretty interesting. If we start to apply force to compress the spring, these gaps in between the coils are going to slowly become less. And they would come a certain point when, let me erase this. I don't need this. There would come a certain point when these wires are going to be stacked one beside another one. For example, something of that sort. Let me use a bit thicker pen so that I can make sense of what this is the one of the line, and then there is another spring body wire, and there's another wire, 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 there's another wire. Do you understand what I'm saying? If all of these gaps go away, what's
No,
going to
sir.
happen? The coils are simply going to touch each other side by side, pretty much like whenever pretty much like the fingers. If you are making a fist, other than the thumb, there's the fingers. So they're going to pretty much touch each other side by side. So at this point, if we still try to apply force onto this object, this is not going to behave like a spring. Now it is pretty much like metals are stacked upon each other. So up till these gaps are available, it's going to behave like a spring. Whenever these gaps become zero, this is going to work like a hollow cylinder, solid hollow cylinder, because the metals are not touching metal. So now it's not going to behave like a spring anymore. It's going to behave like a much more stronger object. So if we try to draw a graph of force versus
Sir,
length, just a second, Yusuf, if we try to draw a graph of force versus length for a compressive string scenario, it might start from a pretty large length, and then for a certain part, it's going to behave linearly. But the moment these coils are going to start touching each other, the graph is going to almost start to take a vertical rise. Because in that case, even though you are going to start to, if you keep on increasing the force by a very amount, compressive stress by very amount, you're going to observe very little compression any further. So you're going to have a linear graph till the point you have the gaps between the coils. The moment the gaps are gone, the spring is going to start to behave like a very stiff object, and it's likely to behave so. এই ভার্টিক্যাল নিয়ার ভার্টিক্যাল রাইজটা কি বোঝা যাচ্ছে কেন হচ্ছে এটা? ফিজিক্যাল রিজনটা বোঝা গেছে কিনা? হ্যাঁ, ইসু কি যেন বলতেছিলা?
sorry, think I got my answer. I mean, that basically we are deciding the graph of a spring when it is compressed rather than stretched, right, sir?
আরেকবার বলো, আমি বুঝি নাই, প্রথম পার্টটা বুঝি নাই, আরেকবার বলো।
Sir, we are determining the graph of spring when it is compressed, right, sir?
Yeah, that's the
Rather
example that I'm
stretched.
giving this now. Yes, other than spring stretch. If we're stretching a spring, we're gonna pretty much get a graph that's somewhat similar to this one. I mean, stretching a spring, stretching a wire, they all pretty much come up with the same shape of graph. But if you're doing compressing, then we're gonna have some significant change of deformation, something of this sort.
Sir, one more thing. Won't over here in the graph, won't we have a like sharp change in
Gradient.
sharp change?
Yeah,
Yes, sir.
ideally,
Sharp change in gradient.
yes, I definitely agree to this point, because a spring is supposed to behave like a permanent, I mean, as far as I have seen, I mean, so far as my experience goes, any spring that is manufactured is designed to behave like an elastic material till the last point of its compression. I mean, whenever the coils touch each other, within this point, it very well behave as an elastic spring. If that's the case, then we might actually have a really sharp point over here. I mean, there might be a very beautiful straight line, and there might be very sharp going upwards like that. But point to be noted, if we zoom on to this point to a very highly magnitude view, we're going to come up with a curve anyway. If you start to take up very small fractions of increment of force over here, you can actually get a curve. So having a sharp cutoff point might actually mean that it is suddenly increasing, which is actually true. I mean, there will be a sudden change, but if the scale is large, then we are going to see a corner sharp point. If the scale is small, we are zooming in, then we're going to get a curve. That's the best way I can respond to your question.
But sir, why would there be a curve even if we zoomed in? So I mean, it's just limited to us point.
No. That's pretty simple for me to explain. let me give you a different example other than this. For example, let's say we have thrown an object vertically upwards and we're trying to draw the velocity time graph of this object. So we're going to have a graph that looks like this, right? Upward velocity at the beginning, and the object is, this is the maximum point of rise. Now, if we try to draw the distance time graph of this object from the starting point, let's say this is the ground, just slowly going upwards. Initially, you have a very high speed. So what's going to happen? You're going to have a graph that's going to look like this, right? Zero gradient, and then like this. The DT graph is going to look somewhat like that. Vertically thrown object over time. ঠিক কিনা?
Yes, sir.
এখন কথা হচ্ছে এই যে এই পয়েন্টটাতে আমরা পারফেক্টলি একটা জিরো গ্রেডিয়েন্ট পয়েন্ট পাবো না?
Yes, sir. I mean the turning point, sir. Yes, sir.
Exactly. Even if we throw the object to a very high speed, even so, I mean, এখন একটা জিনিস খেয়াল করো, আমরা যদি টাইম এক্সিসটাকে আস্তে আস্তে মানে টাইমের এরিয়াটাকে আমরা সেকেন্ড থেকে মিনিট, মিনিট থেকে আওয়ারে কনভার্ট করলে আমাদের এই স্প্যানটা আস্তে আস্তে ছোট হয়ে আসবে। সো হ্যাভ এ লুক, ইফ আই ড্র দ্য গ্রাফ, সেম গ্রাফ, এটা ছিল মনে করো টাইম ভার্সেস সেকেন্ড ছিল। এখন যদি সেম গ্রাফে যদি টাইম ভার্সেস মিনিটে আঁকি, তাহলে আমার এই গ্রাফটা দেখতে কিরকম হবে? দেখতে অনেকটা এরকম হবে। গ্রাফটা বুঝে যাবে, but at that point you're going to start to get a more cornered view compared to this wide shallow, ঠিক না?
Yes, sir.
আর এইটাকে তুমি যদি আরো বড় করো, মানে ফর এক্সাম্পল এটাকে যদি আমি এখন মিনিট থেকে যদি আওয়ারে নিয়ে যাই, আওয়ার থেকে যদি ডেতে নিয়ে যাই, তাহলে আমার এই স্প্যানটা আস্তে আস্তে আরো কমতে থাকবে। It is very much possible that if you increase the scale of the time value to a significant amount, it is very much possible that this graph might start to look like a very thin based high peak object graph, right? That ঠিক না?
Yes, sir.
That's the point that I'm trying to say, that if you zoom on it or use a small scale, then that's going to appear like a curve. Does this example make sense with you?
So, sir, it becomes a curve because probably the material does not exactly allows us to squeeze the spring even further.
Yes, you can say that. Yeah, that's the correct response. I definitely say it's a correct response. Okay, that's a pretty interesting question. I'm happy that I could explain this. Maybe not so satisfyingly, but I tried. Any questions so far, Polaban? Have a look at this whole thing if you have any question. The next thing that I'd like to discuss is what happens for polymeric substances. So polymeric substances are pretty nuts. They are beautiful. Polymeric substances. Let me tell you what polymeric substances are. Whenever we discuss materials, there are basically three type of material bonding that we typically talk about. One is the metallic bond, which are like really metals are pretty much very ductile, or they are also very much malleable. These are the two words that pretty much mean the same thing, but under the effect of two different type of effect. Ductility of a material refers to the ability to become thin wires or to have a large plastic deformation region before breaking. That's important. Ductility of a material means that it has a large plastic deformation region before breaking under the effect under tensile stress. Tensile stress means that if you are pulling the object from two ends or maybe from multiple ends, and before the object actually start to tear apart, before the object start to disconnect anywhere within this length, the object is going to represent a significantly large amount of plastic deformation. So before the object breaks, it's going to start to become wires. So simple thing to remember is that ductility of a material actually means its capability to become wires, whereas malleability, mallus is a Greek word, I believe, which means hammer. Malleability of a material means its capability to undergo large plastic deformation under compressive loads or under squashing effect or under squeezing effect. For example, the mechanism by which metals can be made into thin sheets. You have a metal plate, you apply force with some rollers, you can make it thinner and thinner and thinner and thinner. So that's the deformation under compressive loads. So both of these two things are pretty much related to the same property, same inherent property of the material, that is to the capability to represent large plastic deformation under force. If the force is a tensile force, pulling force, we call it ductility. If the force is pushing force or compressive force, squeezing force, we call it malleability. So depending upon the force applied, we have two different names for it. Metals are highly ductile and highly malleable, both because they have a large plastic region. Whereas there are certain materials which are not so much, which do not show a very high amount of plastic behavior. For example, glass. Glass, if you start to deform it, it's gonna give you some deformation. Now you might wonder, glass undergoes deformation? Since when? Well, they do. That amount of deformation might be very small. So if you draw a force versus extension graph, you might get a pretty steep line, but it's going to be mostly straight line. The moment the glass specimen starts to go over a very small amount of elastic deformation that it allows, it starts to crack. And the moment it cracks, all of the glass shatters. That's how glass is made. So these are the two different type of materials that you want to recall from your understanding. And there is a third material, which is elastic material, which is the polymer substances. So one that has a large plastic region. Large plastic region means a very huge amount of deformation region whenever load is applied, namely metals, and they have the ductility and they also have malleability. The second behavior is, for one thing that I can also tell you, that certain other materials can also be pretty ductile or malleable. For example, if you think about it, have you kids ever seen any videos of noodles making by pulling? The noodles can be made by hand pulled noodles.
কার্টুনে দেখছিলাম স্যার, বাট রিয়েল লাইফে দেখিনি স্যার।
রিয়েল লাইফে না, মানে ইউটিউবে দেখছো কিনা?
নো স্যার।
হ্যাঁ, মাস্টার শেফে দেখে দেখতে পারো, or ইউটিউবে দেখে দেখতে পারো। So the reason I pulled up this example is that starch can be processed in such a way that it can give us a very large ductile behavior. For example, the dough made from flour, it is nothing like a metal, but it has a very large ductility. For example, if you can roll it enough, if you can shape it properly, and if you start to pull it on opposite sides, you can actually make it a pretty long thing before it actually starts to break off. This behavior is equally applicable for molten glass as well. If you melt glass by applying enough heat and then start to pull apart, you can actually make strings out of glass pieces. So materials can behave differently upon temperature. Temperature is a very important factor, so which is a very, very, very important factor. For example, the reasons metals, irons are actually heated up before they are shaped into something is because whenever they are hot, they undergo more permanent deformation easily. So their permanent deformation becomes easier by applying less amount of force. For example, if you have a solid piece of iron at room temperature, you apply some force, it's not going to behave, it's going to come back. You're going to require a very large amount of force to deform it at room temperature. But if you heat it up a little bit, or maybe a little more, if you heat it up and then start to apply force, you can deform it pretty easily. If you can make it undergo permanent deformation, much too easily. So if you want to reform the shape, if you want to make something else, if you want to make a single bar of iron into a sword or into a scissor or into a helmet, for all I care, then it's easier to achieve this by hot forming or by heating the material. The third type of material that we have is what we call the polymeric substances. Polymeric substances are pretty nice. Polymeric substances are basically the type of materials which has inherently built long molecular chain. Pretty much what you understand from the name polymer. You kids, for those who have chemistry, you know what it actually means. Polymeric chains means materials which have long chains of molecules which are attached one after another. For example, polyethylene is basically polythene, which is the which we use in all of every purposes. Different type of polymers have different properties. For example, polypropylenes are PPs, which can be used for pipe materials. PVC is polyvinyl chloride, which is another type of material, has a bit of benzene cycle within itself. So there can be a lot of different type of polymerization, and different materials have different type of polymeric substances. Polymeric substances have different properties, make them beautiful, make them useful for multiple different purposes. But the bottom line is polymeric substances have long chain molecules which are pretty long. They all behave in a pretty weird way compared to metals or brittle substances. Achha, one thing that I need to show you that I was talking about, that brittle substances, they have a stress strain graph or a force stress strain graph that somewhat looks like this. So they have a straight line and then they cross off, or maybe they have a little bit of curve at the end. So it's also sometimes possible that they might have this and a slight bit of curve and then they break off. So brittle substances have little or no, I mean, they don't have any plastic region whatsoever. They might have a little bit of curve or no curve within their stress strain curve or within the stress strain graph or force extension graph, but they are going to break the moment they are about to go plastic deformation. Glass pieces never undergo plastic deformation, period. Diamond is also a highly brittle substance. It's pretty strong, but it's highly brittle. You have to understand, kids, one thing that I really want to make sense with you. You need to be able not to confuse between strong materials and brittle materials and ductile materials. This is really important. Let me give you a simple example. Anything that can withstand a large amount of force before showing any type of deformation, or any object that takes a huge amount of force to deform even by a little bit, are generally called strong objects. In this case, iron is a strong, normal iron, room temperature iron piece. It's a strong object. Aluminium, quite a strong object. Copper, not so strong. Lead, not so strong. Sodium, very weak. You can cut it by a thin knife. So wood, quite strong. So any object that can take a lot of force before showing any deformation can be considered to be strong. Any object that can show a large plastic region, which means you're applying force to it and you're deforming it, and it is undergoing permanent deformation, it is deforming itself, but it is not getting separated, it's not breaking. That's what we mean by plastic deformation. So ongoing plastic deformation over here that I've loaded over here, that have a look from this is the elastic point in the graph. So এইটুকু হচ্ছে elastic region আর এই পুরোটুকু হচ্ছে plastic region. So breaking এর আগ পর্যন্ত হচ্ছে plastic region. So we only talk about the behavior of a material till the point of breaking. When the object breaks apart, the whole discussion is over. So what is important is that materials, ductility or malleability means objects which can show a large amount of plastic deforming capabilities. In that case, flour dough can be considered to be a pretty ductile material. But is it strong? Can it withstand a lot of force before it starts to deform? No, it's not strong. Do you get my point? These properties of materials or this behavior of materials shouldn't be confused about. I mean, a strong material মানেই যে ductile হবে বা malleable হবে এরকম না. Strong material মানে হচ্ছে যেটা ডিফর্ম করার আগে বা ডিফর্মেশনের সময় অনেক লার্জ অ্যামাউন্ট অফ ফোর্স সে হ্যান্ডেল করতে পারে, সেগুলোকে আমরা স্ট্রং বলতেছি। আর যারা অনেক হিউজ অ্যামাউন্টে প্লাস্টিক ডিফর্মেশন দেখাইতে পারে তাদেরকে আমরা ডাক্টাইল বা ম্যালিয়েবল বলতেছি। So metal strong, ductile, malleable. Whereas on the other hand, diamond or glass is actually strong, but they are brittle. They don't have any plastic behavior whatsoever. You apply enough force on them, they're going to shatter into pieces. And you can glue them back to the same size, because individual pieces are not going to be permanently deformed. But that's not the case for iron. You have a piece of iron, you apply enough force, it's gonna and you cannot simply glue it back because it has undergone permanent deformation. There is atomic level permanent dislocation of the atoms and the molecules, if it's a compound, that has moved with respect to each other, that has given it a new shape, new dimensions. Do I make sense so far? My voice channel ki off হয়ে গেছে?
Yes, sir. You make it, sir.
Here, sir, strong ductile materials are those which can withstand, which have a huge plastic region,
Yes.
and malleable are those which have a huge plastic region. I think I messed up, sir. Ductile is which one is ductile and which one is malleable, sir?
Both ductile materials and malleable materials technically are the same. Ductile materials and malleable materials, they both have large amount of plastic regions. They only have two different names depending upon what kind of deformation are you causing. Are you causing a tensile deformation, or are you extending the object by under pulling forces? In that case, we call it ductility.
Sir, can you repeat this last line?
The large plastic behavior under tensile load, tension, pulling, is called ductility. Large plastic behavior under compressive load or squashing, hammering, that's called malleability. They both represent the same. I mean, within the stress strain graph, they're the same thing. Large plastic region means ductility or malleability. But how do you exhibit? What is the physical process by which you exhibit that plastic region? Based upon that, they have two different names.
Okay, sir. Thank you, sir.
বুঝছো কি clearly?
Yes, sir. Sir, just one more question, sir.
Sure.
Sir, you showed that graph with the when we compress the spring, sir. Sir,
Yes.
ওটা কি একটা sir এটা perfectly straight line parallel to the force axis? নাকি sir, is it a exponential curve, sir?
Well, ideally, it's supposed to be an exponential curve, because if you start to compress the object from this point further, this is going to start to behave like a solid object. I'm going to say from this point, it is going to start to behave like a solid. I mean, just off this point, starting off this point, this is going to be straight line, because this is going to start the this line is basically the force extension graph of a wire for this part. So whenever you are deforming a simple piece of material, so initially you're definitely gonna have a start. We are gonna have a pretty much a straight line, but pretty soon this straight line is gonna start to take curve.
I mean, it's a curve, not a
No,
straight.
there will be a significant portion right of the at the right from the point of change of the direction. A significant portion of this length is gonna be a straight line. Then it's gonna start to take curve.
Oh, acha. Sorry, sir. Thanks, sir.
It will start off as a straight line and then it will start to get. But the length of the straight line is going to be pretty long, because it's going to be almost vertical. I mean, quite vertical, but not essentially perfectly vertical, because that would be impossible, not logical.
Okay, sir. Thank you, sir.
What happens to the polymeric substances? Polymeric substances behave like this. This is the typical stress strain graph or force extension graph of a polymeric substance. While loading, polymeric substances have no straight line portion within their curve whatsoever. So while loading, they follow a graph that somewhat looks like this. So let's say this is loading. What this actually shows us, there is one part that I need you to understand. If you have a force extension graph, try to understand this thing very normally. If you have a object that has a steeper force extension graph, and within the same scale, if another spring has a more slanted force extension graph, how do you describe these two springs? This spring is stronger. Yes, this is one and this is two. Which one of these two springs is stronger?
Sir, it depends on where is the elastic limit, sir. Not on the.
No. I have drawn.
So one is stronger.
One is stronger is the correct response. Can you try to go ahead a bit more for why do you think that? Okay.
So more forces applied to one, causing lesser extension.
Yeah, that's a very beautiful way to say it. So what Ovi just said, Salman, I'm coming to your point. It's not about the elastic point, because I have drawn only the straight line part for two springs. I haven't bent the springs to their limit. But one string is giving us a pretty steep line on the force extension graph. The other one is giving a pretty slanted line. What I'm trying to show you over here, if you want to achieve the same amount of extension for both the springs, let's say if you want to extend both of the springs by this much extension, for spring one, you have to apply how much force? This much force. For spring two, you have to apply how much force? Only this much force. So which one is a softer spring?
They're stronger and more rigid key, same genus.
Yes. Stiff is also a pretty much similar word. Stiff, rigid, stronger. They pretty much represent similar meaning. Whenever, if you ever go into material science, like actual material science is a pretty interesting subject. I sometimes still regret that why didn't I go ahead and pursue that for my master's and everything. But still, material science is a really interesting subject. But if you ever go into this thing, I mean, whenever you get into material science, these words can mean individually different aspect. But for your level, they pretty much mean the same thing. It simply means that the object is difficult to deform. Period. বুঝছো?
জি স্যার।
যেটা ডিফর্ম করতে যত বেশি ফোর্স লাগবে সেটা তত বেশি স্টিফ, বা সেটা তত বেশি রিজিড, বা সেটা তত বেশি স্ট্রং। So if we have two different springs of this manner and we have this force extension graph, we are definitely going to say that spring 1 is stronger or more stiff or more rigid, more strong compared to spring 2. There's two different ways we could explain this. For this blue color, I was trying to explain it that to achieve same amount of deformation, force spring 1 requires a bigger force compared to spring 2. But if you could also try to explain it by a constant force. So let's say if we apply the same amount of force on both the springs, let's say this is the green amount of force that we can apply on both the springs. If we apply same amount of force on both the spring 1 shows a very small amount of deformation, whereas spring 2 undergoes a very large amount of deformation, which means under the same amount of force, spring 2 shows a bigger deformation, proving it to be a more weaker string, or it's a less stiff string. The point that I'm trying to make is that in the force extension graph, the object that gives us a more steep line is difficult to deform. The object or the spring that gives us a more slanted line is easier to deform. এই কনসেপ্টটুকু গ্রাস্প করা যাচ্ছে কিনা? More gradient means difficult to deform, less gradient means easier to deform. এই পার্টটা কি বুঝতেছো সবাই?
Yes, sir.
জি স্যার।
ঠিক আছে, এখন একটা জিনিস দেখো, polymeric substance, let me just write it over here so that we don't forget. Polymeric substances force extension graph shape হচ্ছে এরকম, but this actually goes us to, and over here we have a breaking point. Actually I could draw a break over here. What this shows us that if we start to deform a polymeric substance, in the beginning it behaves as if to be a pretty stiff object. So you can see if I try to draw the gradient over here, and if I slowly start to draw gradient on multiple different locations, you see that the gradient is slowly becoming less up to about this much point. Do you see that? We're losing gradient. And then from here to here, it's almost a very small gradient. So within this segment, it's very easy to deform a polymeric substance. So it's difficult to start the deformation because at the beginning it's pretty stiff. After a little bit of deformation, it's become pretty easy to deform. Right before breaking, it starts to become stiff once again. So before it actually breaks apart, it becomes to deform once again, difficult to deform once again. There is a pretty interesting example that I can tell you, is that this is directly involved for blowing a balloon. If you are trying manually without the help of any power, if you're trying to manually blow into a balloon, you'll find that when the balloon is in its normal shape, like you just took it out of the packet, and you tend to blow it and blow it. Initially it's actually quite difficult to start blowing, but once the balloon, let's say the balloon, let me just try to draw maybe in appropriate shape. Let's say this is an actual balloon. Okay, we have a balloon of this much size. Making this from here, this much size to this much size is usually pretty difficult, but making this from this into the actual size that you want the balloon to be, figure not down to scale, this one is actually quite easy. For those who have blown balloons and you remember the experience,
স্টার্টিং এ অনেক হার্ড।
Yeah?
স্টার্টিং এ অনেক ফু দিতে হয়।
starting on a food exactly. This one is difficult, but from beyond a certain amount, it becomes easier for us to blow. That's basically how the polymeric substances actually behave. That initially they show large stiffness against deformation. Beyond a certain deformation, they becomes easy to deform. And if you have ever actually blown a balloon where the balloon actually popped off, let's say the balloon was actually kaboom, then you might also know that before it actually pops off, it becomes difficult to blow again. You can try it. You can buy some balloon and you can actually physically experience this. But polymeric substances behave this way. And there
Sure.
is almost no definitive straight line within the curve. Although this part pretty much looks like a straight line, but if we actually take graph points of out of polymerized substances, there is no part of the graph that we can definitively say to be a straight line. This is why polymerized substances have no defined Young's modulus. Because you have to understand one thing, just a second, that you have to understand one thing, that elastic limit, the word we use, the Young's modulus, it is the gradient of the straight strain graph for the straight line part of the straight strain graph, or within the proportionality limit of the specimen. Since polymerized substances don't have any straight line part within their graph, the quantity Young's modulus practically don't apply to them. And one more interesting thing is that if you don't deform an object, polymerized specimen up to its breaking point, let's say we're not going to deform a polymerized substance up to its breaking point. Let's say we're going to deform it up to this much force, and then if we start to release the force, if we start to allow it come back to its original shape, it will come back perfectly to its original shape, but it will not follow the original path. It's gonna follow a different path, a lower curve, while unloading. This is what the polymerized substances do. I'll explain this in detail, but before that, I'll take a question. Someone said, "Sir,
স্যার ওই যে আমি বলছিলাম স্যার
বলো।
স্যার পলিমারিক সাবস্টেন্স কোশ্চেন পেপারে কিভাবে দিবে, লাইক কিভাবে বুঝবো যে পলিমার?
Oh, either they'll give you the graph and ask you, is this a polymeric substance, or which of these following graphs represents a polymeric substance? You have to choose the graph, or they're going to tell you that this is a polymeric substance is a graph, and then now you have to answer different specific quantities for this question. For example, what does the area and the graph represent? Which part of the curve represents the energy stored while loading? Which part represents the energy given up while loading? Blah blah blah.
জি স্যার, বুঝছি।
ঠিক আছে? So I have actually tried to show you three different core type of graphs. For example, one of the graphs where you have a large plastic region is specifically for metals. I've written over here. Then you have these two type of graphs, either no curve whatsoever or a slightly little curve before breaking. These are the graphs for brittle substances like glass, crystal, or diamonds, stuff like those. And then you can have the third type of graph where you have a full curve, what's like looking like this. This is a polymeric curve, polymeric substances. Now, pretty much like earlier, if I try to go over here, have a look, polymeric substances behave like this. And the way this behavior is defined, the name of this behavior of going or following two different paths, one while loading and another one while unloading, is what we call hysteresis. This behavior of having two different pathways while loading and unloading is called hysteresis. And this loop that you can see over here, this loop is what we call the hysteresis loop. I mean, this
Loop, sir.
hysteresis, HYS.
No, sir. Where's the loop? Where's the loop you said?
Here, going all the way up and then all the way down. You can go multiple cycles. In that case, you're gonna be following the same thing. This is what we call the hysteresis loop. This closed area. This is somewhat not similar for the case of a metal. Have a look. For the metal, what happened? One path for the loading, a different path for the unloading, and then we have some permanent deformation. But that's not the case for polymeric substances. Polymeric substances would come back to their perfectly original dimension. You can see when the total force is removed, they are still coming back to zero deformation, but only they didn't follow the same exact path. So this is what's gonna happen. Tuck it just a second. While we're gonna do the loading, if we load the polymer substance, let's say from O, let's say this is another point. Let's say let's say this is our point. What? A. I'm gonna give L over here, just a point, and I'm gonna give U over here. So in this case, let's say OLA is the loading curve, and AUO is the unloading curve. Okay, so area under the OLA, let's say that would be, what can I give? B. So this area OLABO, this area represents the energy stored within the specimen while loading or while deforming. So that will be this total blue area that I'm shading over here. This is the total area. This area represents the amount of energy stored within the specimen while the object was deformed or during extension. Then this curve or unloading area, let's say this is the U over here. So let me just draw that U with the red maybe. This is the U, just a point to represent the different line. So area under the unloading curve, which can be represented by A, U, O, B, A. This area represents the energy given up while unloading, which I can shade by red. This is the amount of energy that can be released from the specimen while unloading. So you can see while loading, it takes a bigger amount of energy compared to how much it gives out while unloading. So loading হওয়ার সময় সে এনার্জি নিবে বেশি, বাট আনলোডিং হওয়ার সময় সে এনার্জি দিবে কম। তার মানে বাট আলটিমেটলি আমাদের ডাইমেনশন কিন্তু এক্স্যাক্টলি সেমই অ্যাচিভ হচ্ছে। তার মানে হচ্ছে আমাদের স্পেসিমেনের মধ্যে একটা সাইকেলে ইন ওয়ান সাইকেল মিন্স the process of deforming it once and then getting back to the original dimension once. This is one cycle. In one cycle amount of time, this specimen is going to store this slice area amount of energy within itself. এই জিনিসটা বুঝছো কিনা? লোডিং এর প্রসেসে বেশি এনার্জি স্টোর করতেছে, আনলোডিং এর সময় কম এনার্জি রিলিজ করতেছে। সো প্রত্যেক cycle means in this case one loading and one unloading. That's what we mean by one cycle. So coming back to the original dimension, O point, reaching up to the O point after unloading. So loading and unloading এর সময় আমাদের এই পরিমাণ এনার্জি অবজেক্টের মধ্যে স্টোর হতে থাকবে। This is the amount of energy that we call hysteresis loss. We call it loss because বলো
স্পেলিংটা বলতে পারবেন? হিস্টো
HYSTERISIS. HYSTERISIS, hysteresis. So this loop amount of energy is what we call hysteresis loss. And if we keep on loading and unloading a polymer substance, for example, rubber band, if you have a rubber band, and if you keep doing like extend it and letting it back to the original dimension multiple times repeatedly, then the specimen is going to store this amount of energy within itself for every cycle. This is going to slowly heat up the specimen. This will definitely heat up the specimen. So if we have some polymerized substances which is going to undergo continuous processes of squash and expand, it is very important that those polymerized substances should be cooled properly. Most common example of these things are the tires of every vehicle. Try to think of one thing. A tire looks like this when it's in air. But whenever it is not in air, let's say whenever the tire is actually loaded with a car and the car is on the road, the bottom becomes squashed like that. ঠিক না?
Yes, sir.
তার মানে কি যখন একটা গাড়ি রাস্তায় যায়, whenever a car is going through the road, the part of the tire that is in contact with the road that is actually undergoing some squashing. The moment it comes off the road, it actually gets back to its original position, which means for every single rotation of the car tire, the tire material is undergoing squashing and desquashing, squashing and desquashing. That actually heats up the tire material quite a lot. That the reason the tire actually is not supposed to become that much hot after a very long journey, because they travel through air. Air works as a cooling mechanism. Flowing air works as a cooling mechanism. That's what doesn't heat up the tires a lot. Sometimes heat of the tire is actually also needed, also expected for a better gripping capability of the wheels, which is a very important aspect for Formula One racing, for which they use slick tires with no grooves in them. But there are much more technology for that. But bottom line, do you understand the idea of the hysteresis loss? Hasan bolo.
স্যার ইপিই ইজ কনভার্টেড টু থার্মাল, তাই না? প্রত্যেকটা ইয়েতে যত ফাস্ট করব আমি লোডিং আনলোডিং তত বেশি হিট প্রডিউস হবে।
Exactly. Every cycle of loading and unloading, every cycle will pretty much produce, I shouldn't say pretty much, every cycle for a given specimen will produce the same amount of heat. If you produce more cycles per second, then you'll have a much more heating rate. So how much heat you are producing in terms of power is dependent upon how many cycles are you performing per second.
এটা কি বলা যায় যদি আমরা ইনফিনিটলি হিউজ মানে লার্জ অ্যামাউন্ট অফ সাইকেলস করি, তাহলে ও বি এ যে টোটাল এরিয়াটা ওই পুরাটাই হবে হিট মানে হিস্টেরোসিস লস?
No. one thing that I'm not trying to transfer properly. This blue area is the energy
Yes, sir.
required to extend the polymer substrate. For example, মনে করো, let's say we have a piece of rubber that's of this much length. এটাকে আমরা এতটুকু লম্বা করব। এখান থেকে এইটুকু লেন্থ বাড়ানোর জন্য যতটুকু এনার্জি লাগবে সেটা হচ্ছে ব্লু এরিয়া। আবার যখন
Yes,
এটাকে ছেড়ে দিব, এটা যখন এবার এখান থেকে আবার এই লেন্থ আবার ব্যাক করবে, তখন যতটুকু এনার্জি তার থেকে ফেরত পাওয়া যাবে সেটা হচ্ছে আমাদের রেড এরিয়াটা। ফর দিস রাবার স্পেসিমেন,
রেড এরিয়া ব্লু এরিয়া মানে স্যার এখানে তো স্যার ব্ল্যাক মানে oh I mean sir the graph sir
yes, in the graph.
oh sorry
So when the specimen is going to come back to its original dimension, then we're going to get the red area amount of energy back from the specimen. So after one cycle, this black area amount of energy is going to be stored. So this is a representation for one cycle. If you do this process a lot of times, you're going to simply go through this path OLAUO multiple different times. So as a result, you're going to be storing more and more energy over here, but the graph would pretty much represent the same because the graph represents for one cycle.
জি স্যার, এবার বুঝছি স্যার।
বুঝছো?
জি স্যার, এবার বুঝছি স্যার। জিনিসটা আমি অন্যভাবে চিন্তা করছিলাম, এটা করি নাই।
No, it's okay. So if the cycle is done more repeatedly, then we're gonna be heating it up more. We're gonna be heating it up more rapidly. Essentially, this heat is usually dissipated to the surrounding if it's not too hot. But if it is too hot and if we do not dissipate it carefully to the neighboring areas, then this heat can keep on accumulate within the specimen and can lead to multiple different problem for industrial or vehicle scenarios. One of the first problem that it produces is elastic fatigue, which is somewhat not discussed in the syllabus. I'm just telling you because I wanted to tell you. Elastic fatigue is a bit of a clumsy behavior by rubber materials or polymer substances, and then also enough heat can start to lower their expected quality. For example, we use rubber materials for different purposes in different places. We also change the properties of rubber materials by different amount for our requirements as well. I mean, synthetic leather is also a compound made up of rubber that behaves one way compared to balloon materials, compared to tire materials. So there are different uses. Someone said, sir?
sir so can a rubber start a fire?
Yeah, definitely. If not designed properly, it can definitely start a fire. Theoretically speaking, definitely. Practically speaking, it will be very difficult to do it, to be honest, because I mean, you have to have a situation where the amount of heat energy that we are storing within the specimen for every single cycle of loading and unloading, if we do not allow that heat to dissipate away, then you can slowly accumulate the heat and you can raise the temperature high enough so that you can make a fire out of it. But if you cannot store the heat within the specimen, if the heat is getting lost by radiation, conduction, or convection, any of the three processes of the heat transfer, then you are not going to be able to reach to that high temperature. I mean, if heat is not lost, you can definitely make a fire. You can make a pretty high temperature. If heat is lost, then no. বুঝছো?
Yes sir
স্যার, এটা এভাবে পসিবল করা যায় না যে আমাদের there is this two-dimensional thing যেটার ভিতরে একটা পিভট লাগানো থাকে, আর এটা রোটেট করলে তাড়াতাড়ি একটা কেওস সিস্টেমের মতো মুভ করে ভেরি ফাস্ট, তাহলে স্যার করা যায় না?
I know what you're talking about. Possible to achieve a system like this, but I mean, there can be a lot of different technical aspect involved in this consideration. One that I can think of right now, right off my brain, is that if we want to make it enough hot, we have to be able to store that heat. That's what I can logically think about, for which I believe I'm pretty correct. But there can be other aspects involved as well. Achha,
Yes, sir.
I'll take a very small break and I'll be right back with the lecture. So elasticity chapter key discussion আমাদের actually প্রায় শেষ। আমি এখান থেকে তোমাদের কিছু MCQ দেখাবো যেগুলা to some extent একটু confusing হতে পারে। I'll be right back. আচ্ছা, let me pull up some questions. ও আচ্ছা, আরেকটা জিনিস পড়াতে ভুলে গেছি, যেটা হচ্ছে বেন্ডিং এর সময় কি হয়। Let me go through this one. The other thing that is included in your syllabus, a super interesting thing, is any specimen, whenever we apply axial load, it will undergo total extension or total deformation. For example, let's say we have a metal piece over here like this. If we apply load like this, which is called tension, the object is going to undergo extension. If we apply load the other way around, let's say if we apply load like this, the specimen will go compression all over its length. What about if we have a specimen like this and we apply load like this? Then the object will bend. And what happens in a bend specimen, or not necessarily an object that is appearing to be bent, but forces which are trying to cause it to bend? How do the bending of a specimen work? এটার জন্য খুব চমৎকার একটা গ্রাফ আছে আমাদের বইতে, আমি সেই গ্রাফের বইটাই বের করি। দাও
স্যার ওই নতুন বইয়ে
বইতে আছে, আমি নেট থেকে বের করতে পারবো। দাও this is the part. You don't need such a detailed graph for your syllabus, but the gist is here. So let me just show you what it means. Whenever an object is bent, for example, let's say this specimen was bent into this shape. So naturally you need to understand that before the object was bent, maybe the object's original shape was like this. Now, whenever we are going to bend this object, the outer part is going to become longer and the inside part is going to become smaller. So try to have a look over here. If you consider that this thing was bent where the faces make an angle of theta over here, in that case, the outer segment is going to have a longer length than the original length, and the inner segment is going to have a shorter length because of the arc radius. So it's equals to r theta. This r is smaller, this r is smaller, whereas this r is bigger. So for the same theta, this is a smaller length, this is a bigger length. So the inside part experiences compression, the outside part experiences tension. So within the same specimen, on two different sides, we can have two different type of compression deformation available. This is a very interesting scenario because in many cases this can lead to mechanical failure or breaking of a specimen pretty easily. Pretty easily means, come to think of it, I mean, if you have a ruler, let's say if you consider a plastic ruler, 6-inch ruler, if you try to pull it to in opposite sides by your hands, you cannot break it. I assume that you cannot break it. I cannot. If you try to push it from along the length, you cannot break it either. But if you start to bend it by putting your thumb at the inside, somewhere close to the middle, and try to bend it like that, it's gonna break pretty easily. So bending forces are pretty important in considering for the design of materials. And there is a way, I mean, the reason bending actually causes such high amount of breaking tendency is because of the mismatching of stress within the same specimen over such a small thickness. For example, let's say this is actually a cylindrical wire. Maybe the diameter of the cylinder is maybe 1 centimeter. But if we have 1 centimeter material bent in this fashion, the amount of tensile stress over here is going to be pretty strong, and the compressive stress over here is going to be pretty strong as well. So within a very small thickness of material, you're going to have two opposite type of stress built up, causing to a much more prone scenario for breaking. Now, you might wonder, how can we avoid that? Or what is the most likely case that we can avoid that? There is a common example that I'm going to pull, and I'm going to ask you to think about it. Ooh. Heavy-duty crane cables are made like this, not a single piece of wire, or like this. Can you guess why? What I'm trying to ask you is that whenever we have cranes like this, let's say there is a pretty large heavy crane or heavy large crane, there are cables over here for by which this crane is hanged. We don't have a single piece of metal that is being used as a cable. Rather, we have very thin strands of metals which are wound together in a rope-like structure, which is gonna be used, which has a structure like this. Why? The reason is very simple. They produce a much smaller bending stress. Exactly. Because have a look. Other than having this whole cable of this much shape, if I intentionally sliced up this whole material into thinner slices, very thin slices, and then do the bending, then I'm not going to get a shape like this. Rather, I'm going to get a shape somewhat like this. ঠিক না? এরকম আসবে না?
Yes, sir.
অ্যাডভান্টেজটা কি হচ্ছে? অ্যাডভান্টেজটা হচ্ছে whenever we are slicing up the whole thing in such smaller pieces, we're allowing these individual layers to have a little bit of sliding across each other. Here, there was no sliding allowed. All of the layers are practically stuck with each other. That's why the whole thing had to bend, and we had a pretty large angle produced over here. But whenever we have a scenario like this, all of these individual layers can slide past each other, and as a result, they are all going to develop a much smaller amount of difference of tensile and compressive stress across themselves. This is why cables, in industrial or heavy duty cables, they are not made by a single piece of rod-like iron piece. Rather, they use many small diameter wires which are wound together like a rope. মনে করা হচ্ছে একটা ইন্ডাস্ট্রিয়াল কেবলের রোপ। এটার মধ্যে একটা ওয়্যার সেটা এভাবে পাস হচ্ছে, কারণ এটা অনেকভাবে পাঠানো হচ্ছে, আর একটা ওয়্যার এভাবে পাস হচ্ছে, আর একটা ওয়্যার এভাবে পাস হচ্ছে। সো সবগুলো ওয়্যারে কি হচ্ছে, দেখো একটা জিনিস খেয়াল করো, one single wire that is on this side and also on this side, also on this side. So whenever this cable undergoes deformation, let's say whenever I'm gonna bend this cable, let's say if I bend this cable, one wire is going to experience tensile load on this part, it's going to experience compressive load on this part, but it's not going to actually has to undergo this compression and extension because it can deliver the extra length needed on the outer side, and it can take less length over here on the inside. So it can simply give out the length in the necessary places, ultimately keeping the average length same over the whole cable. And this is why all of these industrial cables, if you look over here, you'll see that these cables are not essentially dry. They are highly lubricated. I cannot find a picture where this lubrication is very vividly represented.
যে গ্রিজিং করা থাকে
হ্যাঁ, গ্রিজিং করা থাকে এক্স্যাক্টলি। গ্রিজটা করার কারণ হচ্ছে যাতে করে ওই ইন বিটুইন ওয়্যারগুলো যাতে একটা একটার সাথে মুভ করার সময় যাতে ফ্রিকশন না হয়, সো দ্যাট দে ক্যান ফ্রিলি মুভ অ্যাক্রস ইচ আদার।
স্যার আমি এক্স্যাক্টলি স্যার বুঝি নাই স্যার, মানে কেন আমরা এত লেয়ার লেয়ার করি স্যার?
Somewhat like this. A very sticky grease is used so that these individual wires can actually move past each other with little resistance across their sliding surfaces. এই পার্টটা কি বুঝা গেছে বলাবান?
না স্যার, এখন একটু ক্লিয়ার। মানে স্যার লেয়ার এরকম মানে একটার পর একটা কেন করি স্যার এক্স্যাক্টলি স্যার?
আচ্ছা, whenever the total thickness of the material is large and we bend the whole thickness of the material, then we produce a very large, we produce a pretty steep angle for the two surfaces. But if we have the material, but for example, আমি এটা বুঝাই তোমাকে, মনে করো আমাদের অবজেক্টের নরমাল লেন্থ হচ্ছে এইটুকু, এটা হচ্ছে মনে করো আনডিফর্মড রিজিয়ন, এটার উপরে হচ্ছে টেনশন, নিচে হচ্ছে কম্প্রেশন। এখন এই লাইনটার লেন্থ মনে করো হচ্ছে এল, এটা মনে করো হচ্ছে এল প্লাস এক্স, এটা হচ্ছে মনে করো এল মাইনাস ওয়াই। বুঝতেছো কি বলছি?
ইয়েস স্যার।
আচ্ছা, এক্স আর ওয়াই ইকুয়াল হবে না, আইডিয়াল কেসে ইকুয়াল হয় না, ওই জন্য আমি দুটাকে ডিফারেন্ট ভ্যারিয়েবল দেখাই। এই যে অ্যামাউন্ট দুটার যে ভ্যালু, এই ভ্যালু দুটো যত বড় হবে আমাদের এটার ব্রেকিং টেন্ডেন্সি তত বেশি হবে। দ্য টোটাল অ্যামাউন্ট অফ
কোনগুলোর ভ্যালু স্যার? এক্স আর ওয়াই এর ভ্যালু?
এক্স আর ওয়াই ভ্যালু যত বড় হবে, I mean the total amount of mismatching deformation, extension on the outer side and compression on the inside, এই দুটো ভ্যালু যত বেশি লার্জ হবে, the material is going to be more prone towards breaking. Think about the example that I gave you for the ruler. If you have a 6-inch ruler and if you try to apply, if you try to bend it, the more you bend it, the more likely it is to break, and there will come a certain point beyond which it is going to break at multiple points, right? So the more you bend it, the more stress you build up within the material, and that leads to breaking. So আমাদের এইমটা হচ্ছে যে এই দুই সারফেসের মধ্যে যাতে বেন্ডিং যত কম হয়, and ম্যাটেরিয়ালটা যদি এতটুকু বড় না হয়, এই ম্যাটেরিয়ালটা যদি চিকন একটা ম্যাটেরিয়াল হতো, ফর এক্সাম্পল ইফ ইট ওয়াজ দিস মাচ থিন অফ এ ম্যাটেরিয়াল, তখন এটাকে বেন্ড করলে কি হতো? তখন বেন্ড করলে মনে করো হচ্ছে এইটুকু হইতো, বেন্ড হয়ে মনে করো এইটুকু হইতো। এখন তুমি যদি চিন্তা করো, লেটস সে উইদিন দিস ম্যাটেরিয়াল, লেটস সে দিস ইজ দ্য আনস্ট্রেচড লেংথ লাইন, original length line আমাদের এই বরাবর আছে, this is L. Wouldn't this thing, let's say this is L plus x prime, and let's say this is L minus y prime, এই x prime x এর থেকে অনেক ছোট হবে না?
Yes sir.
So that's the whole point. So if we have small thickness of materials which are being bent, then the individual buildup of stress is going to be smaller. So what is happening over here, all of these individual wires could slide passes. So over here we're going to have stacks of wires which is going to stick out like this, one after another. ঠিক না?
Okay sir.
এটা হবে কিনা? Whereas so এই জিনিসটা হওয়ার বেসিক মিনিংটা কি? মানে হচ্ছে কি এই লেয়ারের মধ্যে আমাদের একটু স্লাইডিং হয়েছে, this wire, this lower wire could slide past the upper wire because they are not actually touching each other, because we individually separated them out, which couldn't be achieved for a composite, for a whole scenario like this. So that's the advantage of having thinner materials bending. This is why ropes are made out of thin wires coiled together rather than using a single piece of large material. বুঝে গেছে?
So sir, by using multiple sheets and combining them, we can get our desired thickness, whereas not breaking the.
Precisely.
Okay sir.
Beautiful. What you just said is exactly the thing that I should have said, but beautiful. So এটা গেল এটা। আচ্ছা, কিছু কোশ্চেন তোমাদেরকে দেখাই। ফর এক্সাম্পল এখানে এটা দেখো, Nylon breaks when the stress within it reaches 110 Pascal. Which range includes the heaviest load that could be lifted by a nylon thread of diameter 1 millimeter? এটা হচ্ছে ব্রেকিং স্ট্রেস। সো 1 মিলিমিটার দিয়ে ম্যাক্সিমাম কত 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 রেঞ্জের কত নিউটনের লোড উঠানো যাবে হিসাব করো। আমাদের ফর্মুলা হচ্ছে কি F equals to সরি সিগমা ইকুয়ালস টু হচ্ছে F ওভার A, তাহলে F equals to হচ্ছে সিগমা ইনটু A, সিগমা হচ্ছে 1 to the power 1 to the power 9 মাল্টিপ্লাই বাই কস সেকশন এরিয়া। এখানে এরিয়া দেওয়া আছে হচ্ছে আবার মিলিমিটারে, এটা মিটারে কনভার্ট করা লাগবে। এটা আবার দেওয়া আছে ডায়ামিটার, তার মানে এটা হবে হচ্ছে পাই ইনটু 0.001 ডিভাইড বাই 2 হোল স্কয়ার। বুঝছো কি বলবান? ডায়ামিটারকে রেডিয়াস বানালাম, পাই আর স্কয়ার করলাম, মাল্টিপ্লাই বাই দ্য স্ট্রেস ভ্যালু করে ধরো এটা কত আসে।
Sir, 255, sir.
2
Yes, sir, 785.
Yes, sir. 785 অথবা 55.
I'm getting 785.39 blah blah blah. তো এটা কোন রেঞ্জের মধ্যে পড়ে? সি তে পড়ে না? So C is the correct response. And এখানে বলছে হচ্ছে which range includes the heaviest load that could be lifted. So এই রেঞ্জের মধ্যে heaviest loadটা আছে। Now you shouldn't lift, or we cannot lift more than 685, but I mean this is the maximum load that can, but this is belonging to this region of load representation. তারপর মনে করো এটা আছে a piece of copper is drawn into a continuous wire, which behavior is the copper exhibiting? It is acha try to answer the question. A piece of copper is drawn into a continuous wire. So what kind of deformation does this represent? You have a piece of wire which was covered into wire. Are we talking about elastic deformation or reversible deformation? Are we talking about plastic deformation or permanent deformation? What do you think?
Sir, I didn't get the statement. A piece of copper is drawn into a continuous wire, sir.
Yeah, so you have a piece of copper which was eventually converted into a wire, continuous wire. It didn't break. So what kind of deformation are we talking about within this picture?
Sir, plastic, sir.
Definitely. So what is your correct response?
Sir, C, sir.
C.
There we go. Okay, number 3 is a pretty interesting question. Have a look at number 3. A simple crane consists of a rigid vertical pillar supporting a horizontal beam. A weight W is lifted by a rope at the end of the beam. What are the forces at point X and Y and Z due to the weight W? And then খেয়াল করো W লোডটা হ্যাং করার জন্য ইভেন্চুয়ালি আমাদের এই ক্রেনের উপরে কিরকম ফোর্স পড়বে?
Sir, sir, that stretching force, sir.
Let me help you. Because of this loading, this part is gonna try to go down. So this whole thing is gonna behave something of this sort. এরকম হয়ে যাওয়ার কথা না?
Yes, sir.
Shouldn't this mean the inside part is gonna undergo compression and the outside
Yes, sir.
part is gonna undergo tension? Because this is gonna be a case of bending. Only in this case, this is not a single straight bar. This is a L-shaped bar. So all of the inside part is gonna undergo compression, and all of the outside part is gonna undergo tension. So force at X is tension, forces Y is also tension, forces Z should be compression. Which answer choice does have that? X is
B.
tension, tension. B. B is the correct response. বুঝা গেছে কিনা?
Yes, sir.
কারো কোশ্চেন থাকলে বলো, I'll help you understand better. আচ্ছা, এইটা দেখো, which properties best describe modeling clay? Modeling clay basically means the modeling clay হচ্ছে ওই যে modeling clay মানে
স্যার খেলার জন্য ওই ক্লেটা স্যার
play dough, that thing. Which one do you think that represents?
কে হবে
ডি
স্যার?
কি হবে?
Well, here's
ভেঙে
the
যায় না
কি
স্যার?
হবে স্যার?
বুঝি নাই।
অল্প ফোর্স দিলে ব্রেক করে না?
No.
তুমি প্লেডো দিয়ে খেলো নাই কখনো?
ডি
Okay.
স্যার,
খেলছি, ব্রেক করে তো মানে আস্তে।
ল্যাবে ইউজ করা নাই।
You have some modeling clay. You apply some force. Is it going to immediately separate or is it going to first deform into a
আগে
flat
একটু
thing?
স্কোয়াশড হবে স্যার, তারপর।
So before breaking, does it represent a significantly large plastic behavior?
স্যার ইলাস্টিক।
Elastic behavior would mean that if you remove the force, it should come back to its original shape. Does modeling clay behave like that?
ও স্যার,
নো স্যার,
এটা স্যার
প্লাস্টিক।
প্লাস্টিক
Besides,
স্যার।
it behaves as a plastic and ductile material. Ductile because, like I said, ductility means what? A large plastic behavior before breaking. It doesn't have to be reversible. Because plastic behavior does necessarily mean that it is not reversible. Plastic deformation means permanent deformation. So modeling clay represents the behavior of plastic and ductile behavior. So D would be my response. The answer কি দেখো তো D দেওয়া আছে কিনা? Answer কি আছে কারোর কাছে?
ডি।
D আছে?
জি স্যার।
আচ্ছা, তাহলে তো হইছে। Okay, number 5 টা একটু দেখি। 4 is actually pretty simple. What is plastic deformation? This is a definitive question, definition based question. Have a look. Plastic deformation occurs when strain is not proportional to stress, but when the load is removed, the material returns to its original length. No.
নো স্যার।
Plastic deformation occurs if the load is removed, the material contracts, but a permanent stretching has occurred. This sounds about correct. So this might be the correct answer unless there is better option. So let's have a look at C and D. Plastic deformation occurs until the extension is no longer proportional to the load. Not necessarily.
স্যার নট নেসেসারিলি মানে স্যার বুঝলাম না স্যার।
বলতেছে plastic deformation occurs until the extension is no longer proportional to the load. What you need to understand that proportional means the line has to be straight. Have a look. What happens for the metals? If you consider the force tension graph or stress tension graph for metals, we have a straight line part. At the end of the straight line, there is a P point, which we call the limit of proportionality. Then starts the curve. A little bit into the curve, there is an elastic behavior, which is over here. Within this curved portion, a little bit of curved portion, the force and the extension are not proportional because this is a curved part. But within this part, the deformation is still reversible. Do you get my point? Force and
ইয়েস
extension
স্যার।
proportionality লুজ করার সাথে সাথে কিন্তু আমাদের ইলাস্টিক বিহেভিয়ার গায়েব হয়ে যাচ্ছে না, কারণ এইটুকু কি রিপ্রেজেন্ট করে? ইলাস্টিক বিহেভিয়ার রিপ্রেজেন্ট করে না।
ইয়েস স্যার।
So physically, proportionality doesn't define elasticity. Elasticity is a physical behavior that is exclusively defined whether the deformation achieved is reversible or not. If the
Okay.
deformation is reversible, it's elastic deformation. If it is permanent, somewhat, I mean, use the word somewhat because not all the deformation becomes permanent, because you need to understand that if we remove the object's load from this point, the object does not hold back all the deformation. That doesn't happen. The object follows a parallel path and some deformation is held back, তাই না? বুঝছো কি বলছে? আমি
Yes, sir.
মানে
Yes,
ইলাস্টিক
sir.
পয়েন্টের বিয়ন্ডে ডিফর্ম করলে অবজেক্টের মধ্যে যে পুরো ডিফর্মেশনটাই তার মধ্যে থাকবে, ব্যাপারটা এরকম না, কিছু ডিফর্মেশন তার মধ্যে থাকবে। সো সাম অ্যামাউন্ট অফ দ্য ডিফর্মেশন উইল বি রিমেইনিং অ্যাজ পার্মানেন্ট ডিফর্মেশন। সো সি ইজ নট কারেক্ট বিকজ সি ইজ টকিং অ্যাবাউট
Okay,
only the proportionality. দ্বিতীয় বলছে plastic deformation occurs when the material extends so that the strain is directly proportional to stress. No, B is the only logical choice here. 7 নাম্বারটা ট্রাই করো তো বলাবান, দেখো তো 7 নাম্বারটা বুঝে যায় কিনা।
ডি হবে।
পরে দেখো।
এটা তো রিটার্ন করবে না স্যার, ইলাস্টিক হইলে টু ইটস অরিজিনাল শেপ আর plastic হলে it will change permanently.
এই তো so elastic and plastic behavior is not defined by the linearity or proportionality behavior. It's defined by the physical achievability, whether the deformation is reversible or not. আচ্ছা
স্যার হবে স্যার আনসারটা
এটা কারেক্ট আনসার হচ্ছে ডি
but sir the other options were quite confusing though.
বিকজ সব অন্য অপশন বলতে সবগুলো কারেক্ট না which to best define
Yes, sir.
elastic and plastic behavior. Elastic behavior means that deformation is reversible. Plastic behavior means deformation is somewhat permanent, somewhat.
Yes sir.
So extends only within the limit of proportionality. That's not correct. Materials which extend only within the limit of proportionality can be said to be brittle substances, not necessarily elastic behavior.
Okay sir.
Elastic behavior is not defined by the property of the graph. Elastic behavior is defined depending upon the type of deformation.
So sir,
বলো।
A's elastic definition says that they will only extend as long as they're elastic, not I mean about over that they won't exist. I mean the graph won't exist.
Brittle substances.
Yes sir, I mean this is brittle.
Yes. Brittle substances will break pretty much right at the proportionality limit, or they might have a little bit of curve, but they will definitely break at the elastic limit. I mean, for
Okay,
some brittle substances, the limit of proportionality and the limit of and the elastic point are pretty much the same point. For example, the way I've shown over here. I mean, brittle substances which actually have no curve behavior. For those brittle substances, the limit of proportionality, the elastic limit, the breaking point, they are all the same point. For brittle substances which represents a little bit of curve, even by a little bit of curve, up till the point the graph is a straight line, that is the limit of proportionality. But this point where they break, that is our elastic limit, and that is also our breaking limit. E and X are the same point, which basically mean they don't have any plastic behavior whatsoever.
Okay sir, thank you sir.
Sir,
বলো।
স্যার এক্সামের যে পেপার গুলো এটাতে জুমের লিংক সেন্ড করতে পারি পিডিএফ ছাড়া, তাহলে মেমোরি কম হয় স্যার।
বুঝি নাই।
ওই যে জুমের লিংক পাঠাইতে পারবো, জুম না সরি ক্যাম স্ক্যানারের লিংক পাঠাইতে পারবো ওই যে মেসেঞ্জারে ইনস্টেড অফ দ্য পিডিএফ।
আচ্ছা, এটা একটু পরে তোমাদেরকে বলতেছি। পরীক্ষা দিলে আপাতত তোমরা ক্যাম স্ক্যানার করে পিডিএফ করে স্টোর করে রাখতে পারো। এটা কোন মেথডে আমাকে সাবমিট করবো সেটা একটু পরে আলাপ করতেছি। আচ্ছা, এই কোশ্চেনটা একটু দেখো, এটা আলাপ করে আমি আজকে ক্লাস ক্লোজ করবো। এই কোশ্চেনটা একটু পড়ো সবাই, খেয়াল করো। এখানে গ্রাফের এক্সেস হচ্ছে টেনশন ভার্সেস লেংথ। গিভ ইট এ গো।
স্যার বি হবে।
B is the correct response, but do all of us agree on this one?
একটু পড়ে নি স্যার।
হ্যাঁ, কোশ্চেনটা পড়ো, বুঝার চেষ্টা করো। না বুঝলে আমি বুঝাই দিব, নো বিগ ডিল।
স্যার এখানে স্যার কোনো ইলাস্টিক লিমিট দেখানো হয়নি না স্যার?
No, the object, because the deformation line is pretty much a straight line, so we have to understand that it was deformed pretty well within the limit of proportionality.
Yes sir, বি হবে স্যার।
বি হবে স্যার।
B is the correct response. সবাই বুঝছো কিনা? না বুঝলে আমাকে বলো, তাহলে আমি বুঝাই দেব।
বুঝছি স্যার।
আচ্ছা, ঠিক আছে। আজকে একটু থাক, ইনশাআল্লাহ নেক্সট ক্লাসে আমি বাকি জিনিসগুলো নিয়ে আলোচনা করব। তোমরা ওয়ার্কশিটও করো, পারলে সময় করতে পারলে পরীক্ষা দাও। তোমার স্কুলের পরীক্ষা ভালো হয়েছে?
জি স্যার,
Easy ছিল।
ইউনিভার্সিটি ঝামেলা ছিল।
ইউনিভার্সিটি ঝামেলা হয়েছে?
জি
স্যার
স্যার।
8 মার্কের একটা কোশ্চেন দিছিল, এটা অনেক হার্ড ছিল, লাস্টের মোমেন্টে গিয়ে পারছি স্যার।
কোন কি টপিকের উপর কোশ্চেন হার্ড দিছে?
রেজিস্ট